Hi, everyone. Welcome and good evening. My name is Lauren Artilles, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, I'm honored to introduce this virtual event with Cumrun Vafa, presenting his new book, Puzzles to Unravel the Universe, with a special introduction by Harvard's own Melissa Franklin. I hope you're all well and safe. Thank you so much for joining us virtually. Tonight's event is the latest installment in our Harvard Science Book Talk series, which works to bring the authors of recently published science-related literature to our Cambridge community and beyond. Coming up in the series on Tuesday, October 13th at 5 p.m., we'll host renowned neuroscientist Christoph Koch for his paperback release of the book, The Feeling of Life Itself, Why Consciousness is Widespread But Can't Be Computed, in conversation with Harvard Medical School professor Gabriel Kryman. To learn more about this and our other upcoming virtual events, you can visit harvard.com and sign up for our email newsletter, or check out the page harvard.com/science for more info. We also have a Science Research Public Lecture Series YouTube channel where you can view previous talks you might have missed. This evening's discussion will conclude with some time for your questions. If you have a question for Dr. Vafa at any time during the talk tonight, click on the Q&A button at the bottom of the screen, and we'll get through as many as time allows. In the chat, I'll be posting a link to purchase Puzzles to Unravel the Universe on harvard.com, as well as a link to donate in support of this series and our store. Your purchases and financial contributions make events like tonight's possible and help ensure the future of a landmark independent bookstore. Thank you to our partners at Harvard University, and thank you to all of you for showing up and tuning in support of authors, publishers, indie bookselling, and especially of science, because it really, really matters. And finally, as you may have experienced in virtual gatherings these last few months, technical issues may arise, and if they do, we'll do our best to resolve them as quickly as possible. Thank you for your patience and understanding. So now I'm excited to turn things over to my partner in the Harvard Science Book Talk series, renowned experimental particle physicist and Harvard physics professor, Melissa Franklin. The digital podium is all yours, Melissa.
Hi, good evening. Thank you for coming tonight. We have something very exciting. I think it's very exciting. Cumrun Vafa is my colleague in the physics department at Harvard. And I remember about 10 years ago, I think, he decided to teach a freshman seminar. That's a class for 12 students who are freshmen on puzzles. And I was very excited, and I wanted to see the lecture notes, which he gave me. So I was able to read this book a long time ago. But I read it again recently, and it's even better. Interestingly enough, so many people wanted to take this freshman seminar that in some years, Cumrun was teaching 3 groups of 12 students every week, which is pretty, you can tell that people really, really liked it. It's an interesting book because even if you don't like puzzles, it's really good. And that's strange because there's lots of scientists and lots of people who aren't puzzle people, but the puzzles in this book are so deep that it almost seems like they're not puzzles. But then again, for the puzzle people, it's even better. So who is Cumrun Vafa? Cumrun Vafa was born in Tehran and went to high school there, and then went and did his bachelor's degree in math and physics at MIT. Then he went to Princeton, and he worked with his thesis advisor there for the PhD was Ed Witten, very famous string theorist. And then he came to Harvard in the Society of Fellows as a junior fellow for 3 years. And straight from that, he was asked to be a faculty member in the Harvard physics department. So Cumrun has been here for the past somewhat 25 years or so, 30 years, teaching, an excellent teacher in our department, and at the same time, winning an enormous amount of prizes. So he works on quantum gravity. We don't actually have a theory. Maybe this is wrong, but I don't think we have a tested theory of quantum gravity yet, and string theory. And he's very famous for, with Andy Strominger, calculating the entropy of a black hole, and for something called F theory. He has won the Breakthrough Prize twice, the baby one and the big one, and the Dirac medal. Dirac was the very famous theorist who introduced antimatter. He won the Heinemann Prize. He's in the National Academy of Sciences, but the best prize of all is he was awarded the Ellis Island Medal of Honor, I assume for being a fantastic immigrant to this country. So here we go. Let's welcome Kumran Vafa telling us about puzzles.
Thank you very much, Melissa, for this very kind introduction. It's a pleasure here to present my book at the famous Harvard bookstore. So let me share my screen. I hope you see my screen here. So I'm going to talk about my book, which is Puzzles to Unravel the Universe. So many deep ideas in physics are related to simple mathematics. And there are simple truths behind deep ideas. And it is these simple truths that many scientists are interested in crystallizing and understanding, and not so much the technical details that go with the mathematical formalism. Luckily, these core ideas are illustrated through simple mathematical puzzles, can be illustrated through simple mathematical puzzles, even for areas as mathematical as my field, for example, string theory. And this is the aim of this book. In fact, the idea, as Melissa mentioned, was the motivation was to make this freshman seminar course, which brings these puzzles and introduces basic principles of physics through these simple math puzzles, beginning in 2012. And the course has grown organically since then with many additional puzzles that students brought to class. And recently I published these notes in the form of this book, Puzzles to Unravel the Universe. And so what I'm planning to do today is to share with you some of the puzzles, just a few of them, a handful of them, to illustrate the flavor of it and how it connects to some of these physics principles. And I hope that this will be interactive. In other words, I'm going to be posing questions and we're going to poll you for the answers. There are going to be multiple questions like A or B or 1 or 2. And it'll be more fun to have that interaction. So that's what I'm planning to do. So the first topic I want to talk about is the notion of symmetry and conservation laws. So symmetry, you have this notion of symmetry, what the symmetric object looks like and what symmetry is. And it turns out symmetry is a very powerful and important concept in physics. And you might think that, symmetry is nice and pretty and all that, but it's a little, you might think perhaps boring. And what can you learn from symmetry? And here I want to illustrate the power of symmetry through this simple puzzle. So here's my first puzzle. We have two containers, one full of green paint and the other one full of white paint. We take a small cup and fill it with the green paint and pour it into the white paint container. And then we stirred it, the container, the white paint container, and we take the same size cup. And now from the mixture, we pour back the same amount of paint back into the purely green paint. And we also stir it. So that is what we just did. And now let it stir very well. Okay, and then what we want to know is which container has the higher concentration of the other color. In other words, does the green container have more white in it, or white container has more green paint in it? And I would like you to answer the poll if possible. So I'll wait till you answer the poll. So let's wait to see what the answer would be. Okay, let's see if the answer is out. So let's see if there is an answer for it. Yes, so the answer is the white-green contains more green paint, is the majority set. And this is actually a natural answer to give for the following reason. You see, the white paint was pure white, and then you took the pure green paint and you poured it into the white paint. So when you brought the container, when you added the green content, it was pure green. But when you brought it back, it was mixed. So there was pure green transported to the white paint, but mixture transported back to the green. So therefore you would think that the green one, the white one has more green in it than the green has the white in it. That's kind of natural expectation. Well, I didn't give you the third option, which is actually the correct option. The correct option is that actually they have the same amount of mixture. In other words, the white has the same amount of green and green has the same amount of the white in it. And the reason is symmetry. So the symmetry in this case is that you start with equal amount of fluid. So the left and the right containers have the exact same amount of fluid. One is green, one is white. So you have the same amount of green, the same amount of white. At the end, when you went back and forth with this cup, at the end, the total volume that you ended up is the same because total volume of whatever you put in, you brought back. So the total volume of the green at the beginning and at the end are the same. So there's some amount of green missing because that amount is in the white. But the volume of the white and the green at the beginning and at the end are the same. So therefore, whatever is missing in one must be in the other and vice versa. In other words, if you kind of do this, if you go, for example, by trying to do the admixture and try to unmix them. So therefore, if we go to the next slide, you'll see, so you just imagine you're unmixing them, then the same amount of white, which is in green, must be the same amount that is the other one. So if you transpose them back to where they are, of course, you go back to the original situation. So they have exactly the same amount of mixture. So the symmetry is powerful, as a simple example illustrate. So symmetries are powerful and they're deeply related to conservation laws in physics. Conservations of momentum, the energy, and all that are related to symmetries. The next concept that I want to discuss is spontaneous symmetry breaking. So symmetries are very, very important, but breaking them, it turns out to be even more interesting and more important for us. So I will illustrate this with another puzzle. So this is the next puzzle. We have 4 cities, A, B, C, and D, on the 4 corners of a square. And we are trying to build a highway system which connects all the 4 cities together. We would like to know what is the shortest highway system we can construct which connects all the cities together. You don't have to directly go from any city to every other city. As long as there's a way from any city to get to any other city through the highway system, that's fine. So we want to find the shortest highway system which connects every city to every other one way or the other. So here's the first question. How many of you think that this is the best route? The best highway system? So yes or no, if you could please give an answer, that would be great. Okay, so most of you say no, and that is correct. How about the next one? Let's go to the next one, which is how about if you just go to this configuration or this one, either of these two. Well, clearly this one is not the answer. So the question would be whether or not if you go to the next one, this one would be, because you can certainly change the number of, you can remove one of the edges and still be the same. Is this the answer? How many think this is the best route? Okay, so again, majority correctly say this is not the best one. And so it turns out, indeed, the best route is this one. The best highway system is this one. And it is surprising. It is surprising because the highway system does not share all the symmetries of the square. You see, if you were lived in the city A and you wanted to get to city B versus city C, you might have thought that since they are equidistant from A, you should have the same time to get from A to C versus A to B. But the highway system, which gives the shortest path between them, does not respect that symmetry. Namely, if you want to get from A to C, it is shorter than from A to B. And so this turns out to be the shortest highway system you can construct. There's another way you can construct it by going from A to B first and then coming down and going from C to D, but either one of them does not enjoy the full symmetries of the square. So this, in other words, the minimum highway distance breaks the symmetry spontaneously. We started with a situation where the square has a certain symmetry, but our answer does not enjoy all the symmetries of the square. Now, the idea of spontaneous symmetry breaking actually is not that new. It has been known for many, not only centuries, many millennia. In fact, the early Greek philosophers already discovered it in the following form. So they were really smart. They had already appreciated that the Earth is round, and they thought it's at the center of the universe. And they had noticed it's not moving, but they wanted to have an argument why the Earth is not moving. They had found its sphere, but they didn't know why it's not moving around. And so to try to come up with an explanation, they said, well, what happens if you think about the Earth as moving somewhere? If you move somewhere like this, then you're breaking the spherical symmetry. In other words, before it moved, you had the spherical symmetry. Every direction was equally good. As soon as you move in some direction, you're picking a direction, you're breaking that symmetry. And they said, you're not allowed to break symmetry. So they tried to explain why the Earth is not moving by trying to use the principle that symmetry is prevented from moving. You cannot break symmetry. So, but they were very sophisticated, and Aristotle did not accept this argument. He said, this is not a good argument, because he argued you could break symmetries, and he tried to explain how could you naturally, spontaneously break the symmetry, and he argued as follows. He said, suppose you have a person at the center of a circle, and you distribute food, like let's say loaves of bread, on a circle whose center is the person standing in the middle, and you ask whether the person is going to move or not. Is the person going to move and break the circular symmetry or not? Or is going to stay in the center? Of course the person is going to move, because the person is going to starve otherwise, so it's going to move at some point. Doesn't care about symmetries if it gets broken, because it's a better outcome to get the food. So the breaking of the symmetry can be done or will be done if there is a good reason for it, and this is an example of it. Similar to what happened in the highway system. So the highway system is an example of it. Now, you might think that these are esoteric examples, but actually there are much more natural examples. Look at your own face. Your own face has two eyes, but you see, we live on a situation, on an environment which is naturally 360-degree rotation symmetry. If it was that, why did our body choose the eyes in the front? We should have had eyes all over in a circular way, right? Like this one, because that would be more symmetrical. So spontaneous symmetry breaking is in fact imprinted on our body. So our eyes are in the front because evolution has decided it's a more efficient way to make use of its resources, because what we really need is to go after the food after all. So we need to know where is the food, and we're going in that direction. So the eyes in the front are more important than all over the head. And so therefore, that's what it chooses. So spontaneous symmetry breaking is a very natural phenomenon and happens again and again, and it's very frequently seen in different contexts in physics. So for example, the applications on physics is enormous. One example is the origin of mass. The fact that we have masses is related to the fact that symmetry has to get broken. Fundamental laws of physics show that if symmetry was not broken, we would have no mass. We would be massless, like photon, which is traveling through the space with no mass, with speed of light. We would have been going with the speed of light if it wasn't for the fact that symmetry has gotten broken. And the manifestation of it is the discovery of Higgs particle that Melissa and the friends discovered in the Large Hadron Collider a few years ago. So this is an example of origin of mass as an example of spontaneous symmetry breaking. Another example is we have more matter We have matter around us, but not antimatter. Naively, you might have thought there's a symmetry, but again, the symmetry gets broken. Magnets, these cool things, you know, they have these magnetic fields in some direction, exist because of spontaneous symmetry breaking. Another cool example is superconductors. Again, manifestation of spontaneous symmetry breaking. So symmetry breaking is also cool and is quite crucial for many different physical phenomena. Now, just to illustrate that math is a lot of fun, and you might think that the more abstract and more complicated the math is, the more fun, and that's not necessarily so. In fact, sometimes very simple, almost trivial math could be amazing and powerful. So let me give you some examples of it. Consider the Earth and the equator, and consider, suppose we have a belt, a big belt, and we wrap it all the way around the equator. And this belt we open up, and so it was originally wrapped tightly around the equator. We open it up, we add 1 meter to the belt, like that, and then we wrap it again around the equator. Of course, now it won't be tight anymore. It will stand a little bit above the equator. So the question is, how much does it stand above the equator? So, so in other words, suppose you have this rises somewhat, and I want to have a question to you, a poll to you. If I try to pass an object under the belt, do you think this object can pass through if it's less than a millimeter, between a millimeter and a centimeter, or between a centimeter and 1 meter? Which one of these three you think is the right one? Okay, let's see what the answer is. So majority of you says between 1 centimeter and 1 meter. Amazing. That is the correct answer, indeed. And it was not the answer I would have expected myself to be given. I would have thought it's much less than a millimeter, naively. And the reason you would think that is that you would think that the belt is extremely, the equator is extremely big, so that original belt is huge, and tiny 1 meter adding to doesn't do much. And so you might think that if you put it back on the Earth, it's just like a micron or some tiny scale up. And indeed, as majority of you correctly said, it's between 1 centimeter and 1 meter. In fact, if you want to see what it is, it's a simple math. Simple math is simply the following. You just consider the circumference, original circumference was 2 pi r, and you add 1 meter, and you want 2 pi times the next radius, which is the radius plus how much it's gotten bigger. So from this simple algebra, you find that 2 pi x is 1, or x is 1 over 2 pi, which is 0.16 meters, or in other words, 16 centimeters. So indeed, it's between a centimeter and a meter. However, I presented this puzzle to my class, and one of the students came back and told me, I got a different answer. I said, how could you? This is simple math. I mean, why did you get a different answer? And the student said that, well, you didn't say that I should put the belt uniformly around the equator. I could, for example, push one side up a little further up. It's like push it one way on the right, and then wrap it tightly around the rest of it. So I said, okay, so what do you get? He said, well, I got 121 meters if I do that. I said, 121 meters if you do that? It's naively just, it's just you have added 1 meter, but you're saying it rises 121 meter? Indeed, the student was correct. It rises 121 meters. And this one is less intuitive. This one needs a little bit of a detailed calculation, but it shows the ideas, simple ideas that sometimes work in simple setup could have amazing extensions, which are very non-trivial looking, like this one. The height that it rises is not like half a meter or a meter, it's about 121 meters. Very surprising. Another example of power of mathematics is the idea of continuity. Physical laws are, set of equations that we typically have, and these equations have solutions which are typically continuous. So the laws of physics give results which are continuous. Things vary gradually and continuously. So that is a typical situation, and I want to illustrate it with the power of this idea of continuity with one puzzle. Consider again the Earth and consider the equator. I love the equator. And suppose we want to measure the temperature around the equator. Could it be that there are 2 points exactly diametrically opposite on the equator, diametrically opposite relative to the center of the Earth, which have the same temperature? Could it be like, for example, this point and that point have the same temperature? Well, it turns out not only there is such a point that they have the same temperature, there always is such a point. No matter what temperature you have on the equator, as long as the temperature varies continuously, it turns out there are at least 2 points diametrically opposite with exactly the same temperature. Now, you might think that this follows from some probably deep property of thermodynamics or atmosphere or whatnot, but it just has to do with the fact that I'm assuming the temperature varies continuously on the equator. And to see that, you just consider the temperature on the 2 opposite points. Let me denote the opposite points by plus and minus. Suppose the temperature on the opposite points are not the same. Well, let's consider the difference between them. Let me call that function f. So if you take the temperature on the opposite point and take their difference, if f was 0, then that's the point where they have the same temperature. So suppose f is not 0, but if I go from theta, if I move around the equator from one point theta to the opposite point, then this function goes to minus itself, because whatever, if this temperature over here is bigger than the other one, if I go to the other side, this one is going to be higher. So the sign flips. In other words, this function flips after you go to the other side, which means that if I start with some value, if it was, let's say, negative, and the other side, it's exactly the minus of it, which is be positive. But since this function is a continuous function, if it goes from a negative value to a positive value, at some point, it will be 0. At the point that it is 0, it will be a point where the temperatures are equal. And so that would be a proof that there will be such points in the Earth. Slightly more interesting extension of it shows that not only there are points which have the same temperature, but if you look at not just on the equator, but on the Earth, there are always 2 points, at least 2 points, diametrically opposite on the Earth, which have exactly the same temperature and pressure. Again, something that you might have ascribed to some deep aspects of physics simply follows from continuity. So another example, which I want to talk about, is gravitational lensing, and how it works as another example of the power of continuity. So first I have to tell you what is gravitational lensing. So Einstein's theory basically tells you that the geometry, the fabric of space is kind of curved, and depending on what objects are where, the curvature changes. So the fact that the space is curved, it means that if you have light rays passing nearby massive objects like galaxies or whatnot, the light does not go straight. It wants to go the shortest path, but the space is kind of curved. So therefore it takes what would be a straight path looks like bent. And if so, it is possible that a given light, a given star emits 2 different lights, which gets to us from 2 different paths because of the fact that the light kind of bends. And this is the situation which is called the gravitational lensing. We can get multiple images of a given object through this lensing phenomenon. So for example, this is an actual example of a picture of a sky. In this picture, you see that there are objects here. They look like various kinds of galaxies or whatnot. And it turns out, actually, in that circle, these 5 blue circles are circled around the same quasar. So these 5 objects here are actually the same objects. Same object. The light is getting to us from different paths, and it fools us to think that they're the same object. And these 3 orange-circled objects are the same galaxy. So the path that the light takes from these galaxies are different, and we think they're actually different, but actually they're the same galaxy. So you see you have 3 images here and 5 images here. Okay, now what does this have to do with puzzles? Well, it turns out that this is an amazing fact, that the number of images that we get, if no image is blocked, of course, somebody could block one of the images. If you don't block any of the images, is always odd. The number of images is odd, like the one we just saw, 3 images or 5 images or 1 image. And exactly less than half of them are inverted. So if you have, for example, 3 images, you have 1 image which is inverted and 2 which is not inverted. And if you have 5, you have 2 inverted, 1 and 3, 3 of them which are not. So why is that? Well, this actually has to do with a slightly more abstract concept in map called the degree of a map. And the degree of a map, which is the number of pre-images of a given point when you have a map from one space to another. So you count the number of points, and that concept, that object, it does not change when you change the things around it. So the number of pre-images doesn't change. Actually, not exactly right. The number of pre-images, maybe the number of points that get mapped to a given point, doesn't change if you count them with a plus or minus sign, depending on whether the orientation of the map is changing near one point or another. So to illustrate it, it's easiest to do it with a picture. So here, you have a picture of the Earth, trying to look at the image of a star, and you see there's one light path which crosses here at one point. Here, it crosses at 3 different points of this boundary of this star, which you would naturally think there are 3 images, and over here, you get 5 images. So you see that if you go around the circle, you get a map from all these 5 points mapping to 1 point, but the orientation is reversing because as you go around this, you go up here, but then down here, and then up here, and then down here, and so forth. So these 3 of them, which are going in the right direction, give you an upside image, right side up image, and the other 2 give you inverted images. And this is illustrated of the fact that the net number of images here is 3 minus 2, which is plus 1, which was the same as what we originally started with. Namely, if you start here from the original one, it was the same number as plus 1, which is the first one we started with. The next example is that I want to discuss, and the next concept I want to discuss is the notion of duality and the physical laws. Duality is one of the basic discoveries that we have made in physics, especially in the past 3 decades. It's one of the driving principles of many areas of physics, and in particular of string theory. And it is perhaps best illustrated with this beautiful drawing of Escher. The duality here is, in this case, illustrated by the fact that even though you have a single drawing, different parts of the drawing give you a completely different image of what's going on. For example, on one side, you think about it's a day, and then you have flying birds, black birds going to the left. On the other side, you're having a black, dark sky, it's a night, and then you have a white bird flying to the right. And similarly, these birds, as you go from up to down, they become fields, the white and black fields down here. So this duality transformation converts this black bird on this side becomes part of the sky gradually when you trace what's happening, and this white bird here emerges from the sky. So there's this duality transformation. One object on one side becomes something else, and the whole thing fits beautifully into one picture, but the objects change their roles. And this happens again and again in modern physics, that objects somehow play a different role, and you have to change the orientation of how you think about them to appreciate the symmetry between the fact that these 2 parts are actually of the same drawing. So here I'm going to illustrate it by one puzzle. So the puzzle is going to have a number of ants crawling on a meter stick. And when the ants collide, the ants are going with a constant speed on the meter stick. The meter stick is 1 meter long. And when they collide, they just reverse direction and go backward. So whenever 2 ants collide, they just change direction and go back until they collide with another ant, and then they go back again. So basically a picture like this. So for example, you see this orange one hits the blue one and then turns back and so forth. It's 1 meter long. So unfortunately, when the ants get to the end, they will fall off the meter stick. So at the end, there would be no ants left. And so the puzzle is the following. Suppose you have 20 ants and you have 1 meter stick, and the ants are going at the constant speed of 1 centimeter per second. Where do you put the ants, and which directions should they initially move so as to maximize the time that the last ant is on the meter stick? Now, one might naively think that you would want to put them all bunched up near the middle somewhere so that they will collide with each other back and forth, so that will lengthen the time they're on the meter stick because of these collisions. The collisions could help you keep the ants going back and forth for a long time. But actually, it turns out that the answer is much simpler. And the answer can be seen just from a duality transformation, changing our perspective. And so the duality transformation that we do is, you see, what we said here is that when the ants move, they change direction when they collide. But if you're not caring about the identity of the ants, if you're just interested in which ant, not which ant, but whether there's an ant on the meter stick, you don't care about the identity of the ant. So you might as well color all of them black. And if you color all of them black, then guess what happens? Then you don't even, when they collide and they go back, you can't even know if they go back or they're just going through each other. So there's no difference whether they're colliding and going back in different direction or just going through each other. Therefore, the answer is simply, you put one ant on the left-hand side of the meter stick and then instruct the ant to go to the right. And then it takes 100 seconds for it to get to the other one. And that's the best answer. No matter what you do, that's the answer that's going to give you the longest for the time for the ant to be on the meter stick. So this illustrates the idea that, a simple change of perspective, in this case, the duality transformation between the identity of the ants, gives you a simple answer of what the puzzle is. So finally, as my last puzzle, it's one of my favorite puzzles, is actually what we always do in science. Namely, what is the scientific methodology? How can you illustrate the scientific methodology with a simple puzzle? And this last puzzle does that. So what do we do? We start with an example or examples, or what we call examples or experiments. So we look at experiments, and after a few of the experiments we observe, we formulate the general principle on the basis of examples. So we see these examples, we say, this is what's happening. And once we understand what's happening and we have these principles, we try to explain why these principles hold. What are the reasons that the things work the way they do? But we don't stop. We never stop. And we ask our experimentalist colleagues, Melissa in particular in this case, to do further experiments and check whether we have made any mistakes. The more experiments we do, the more sure we could be whether we got it right or whether we got it wrong. So here goes the example. We have a circle, and here, the green circle here. And what are we going to do? We're going to choose some points, random points on a circle. So take 2 points on the circle and connect them with the line. So the question is, if I have 2 points on a circle, how many regions do I get inside the circle? Well, in this case, it's kind of clearly 2. So if I have, in other words, 2 points, I get 2 regions inside the circle. Now suppose I add 1 more point. So now I have 3 points, and I add every point to every other point. And then I ask, how many regions do I get inside the circle? Well, as you can naturally check it, it's just 4 regions. 1, 2, 3, 4. So you get the 4 regions here. So 3 points give you 4 regions. Next, you do 5 points. So if you do 5 points, you get, let's count it again, 5 points, you get 8 regions. Okay, so that's good. So 1 more point. So you're beginning to see a pattern, right? Each time you're going down with the number of points, something is happening with the number of regions. So let's do 1 more just to get really the feel for it. So if you do 1 more, this is 5 points, get a little crowded. So if you do the counting, as we have done here, you see indeed it's 16. So what's happened is that each time you add a point, you see what happens to the number of regions. Okay, so now that you have gotten the idea, I'm going to raise the next question. I'm going to add 1 more point. So if I have 6 points, how many regions are we going to get? So I'm going to pose it as a question to you. So let's pull that. Do we get 32 regions, 64 regions, or neither of the two? Exactly. So most of you said 32 is the answer, and 32 is natural as a natural guess because each time you see you're getting double. 2 goes to 4, 4 goes to 8, 8 goes to 16. So it's natural to expect that 16 should go to 32. So let's see if that's actually the case. So you add one more point. Sorry, before we do this, before we add one more point, there's a theory why it should be a factor of 2. So the idea is this: if you just get 2 points connected to a line, each region is either to the left or to the right of that region. So you get a factor of 2 just by counting whether the regions are on the left and the right. And so therefore you also have a theory. The theory says not only is a factor of 2, the explanation is obvious, quote unquote, which is you get the left or right of each region, count the factor of 2, and therefore you're going to get a factor of 2 each time. So you add one more point, and then you look at how many points you get, how many regions you get. And if you count it carefully, hopefully I haven't missed any, but you see that the biggest number I get here is 31. So indeed, the prediction is not 32, it's actually 31. And that's a big surprise. So this is the analog of doing more experiments and finding out that, you know, after all, our theory was wrong. And we have to come up with a better theory to try to explain what the actual experiment is telling us. So we then search and try to figure out what was our mistake, why were we fooled by these experiments to think it has to be 32. And then once one figures out the exact formula, which I don't bother explaining why, you get an explicit formula and in fact gives you 31 as the right answer. And the next one, for example, would have been, instead of 64, it'd be 57, for example. So let me basically end here by saying that I hope I have conveyed the power of simple mathematical ideas in the context of physics. There are many more examples in the book, about 100 or so. And the main thing is that even the most advanced ideas in physics could be illustrated by some fun, simple mathematical puzzles. And I'm thankful that you listened to my talk today. Thank you very much. So let me stop sharing my screen and I will take questions. Okay, so the questions are in the question and answers. So I will look at the questions. In the green and white paint example, are you absolutely sure that mixing is necessary? In fact, it's unnecessary. Good observation. There's no necessity for mixing, and I was just trying to kind of make it more complicated. If it wasn't mixed, it would have been very easy to say it, because then it would be on the top layer, and then you put it back, the top layer will go back from the right to the left. It doesn't matter whether you mix it or not, so that's a good point. Okay, so where do the extra 120 meters come from? That's the question about the equator and the belt wrapped around the equator. Why do we get 120 meters? It is not easy to explain it. It's just that you're pulling one side. Roughly the idea is that the Earth is so big that the other part is basically squeezing the area out from all the other sides and pushing them one side. In other words, when it was equally distributed around the Earth, you had a band around the Earth, which is this extra area that the belt covers. So by squeezing that area all to one side, you're squeezing it a lot, pushing it on one side, and that causes it to rise. But to actually get 120 meters, I don't have any easy way of doing it other than actually doing the math, which involves a little bit of a technical calculation, which is described in the book, but it's a bit too technical to describe it here. So let's go to the next question. Are there examples of actual places on the Earth where there actually are 2 points where the temperature is the same? Does it have to be at the same time as well? The statement is yes. At any moment on the Earth, even right now, there are at least 2 points on the equator which have the same temperature, which are diametrically opposite relative to the center of the Earth. This just follows from continuity of temperature. That's so amazing. So just imagine, like, you open up the TV and listen to the news, and somebody says, you know, amazingly today, it was observed that at any time, people who measured the temperature and pressure across the Earth, they found that there are always at least 2 points which had exactly the same temperature and pressure, diametrically opposite relative to the center of the Earth. And this is a remarkable fact. Well, not really. It just follows from continuity of the physics. And that's the kind of power that math brings in, which kind of clarifies what's going on. So we go to the next question. what is the meaning of the sine curve? I'm not sure which curve are we referring to.
I believe they were talking about the puzzle with the pictures of the different galaxies in it, but I could be wrong.
Oh, the galaxies. Yeah, so
yeah.
The different galaxies, the orange color and the blue color, you mean? Those are the ones? You were talking about the quasars and galaxies. Is that what the question was?
I'm guessing so, yeah.
Yeah, so this is just we're just circling them to just isolate what the quasars, where the quasars are and where the galaxies are. Quasars are the centers of galaxies which are supermassive black holes, and they include, you know, infalling objects, infalling gas and all that, which heats up and glows, and you get all these light coming out of them. They're very powerful emission of light there, and that was the images that was shown over there. In fact, today you may have heard the announcement for Nobel Prize in Physics awarded for the for black holes and the observational aspect as well as theoretical predictions of it. It's a very well-deserved prize.
Okay. I'm so sorry. The person who asked that question just confirmed they were talking about the gravitational lensing graphic.
Yes.
That's
the one we just talked. Exactly. Very good. Okay, so we go to the next question. Do you think we will have a generally accepted theory of quantum gravity in any of our lifetimes? I would say that I think string theory is a generally accepted theory of quantum gravity. And so what Melissa perhaps was referring to is that we don't have a deep understanding of what string theory actually means. That's, in other words, even though we see the facets of string theory give rise to a consistent quantum gravity, we haven't deeply understood all the aspects of the theory. So if your question, so I interpret your question by saying, when will we deeply understand what string theory is all about? And I would say that it's not clear when we will figure it out exactly, but we have already made quite a lot of breakthroughs in my lifetime, and I think that it might go a few more generations. I do not know, but it's quite remarkable journey so far. And in fact, you might think that the longer it is, the more we're going to learn about deep and cool things about our universe. So I don't have a definite prediction other than the fact that we are always deepening our understanding of what quantum gravity is. So somebody asks, Dick asks, could you give a formal definition of symmetry? And indeed, yes, there is a formal definition of symmetry. Symmetry is defined to be doing it in a physical sense. You do an operation on your physical system, and after you do some operation, it leaves it intact. So that's what symmetry is. So for example, if you have a straight line with nothing on it, if you move from one point to another, nothing has changed. That's called the symmetry. So that's called translational symmetry. Or if you move in time from one day to the other, if nothing is specifically happening at a given particular day, shifting the time is a symmetry. Or if you're talking about, you know, a triangle, an equilateral triangle, you have reflection symmetries. When you do reflections, the triangle goes back to itself and so forth, or rotations in that case. Okay, so that's the definition of symmetry. So symmetries imply conservation laws, which is one deep aspect of physics, which is not a priori obvious. So there's a question, besides the examples you have shared today, do you have a favorite puzzle to teach or one you have found particularly helpful in breaking down a complicated concept? Oh, there are many such puzzles. And there are, as I said, about 100 or so puzzles in the book. All of them are cool stuff. I would encourage you to look at them. I don't want to pick a particular one. It's just samples here just to give you an illustration. I would recommend it to look at it. So let's go to the next one. Does all laws of physics relate to symmetry laws and or possible symmetry breaking? So that's by Davud Norouzi. The physical laws, they do not all relate to symmetries. Symmetries are aspect of physical laws, but not the only aspect of physical laws. So symmetry and symmetry breaking are a facet of physical laws, but not the only aspect of them. This is a question that comes from Behruz. I guess my brother is watching it. He's asking me a question. Temperature puzzle, fine and follow, but how about pressure and temperature puzzle? Is there a formula? So the temperature and pressure puzzle is not too difficult, and it's similar to the temperature puzzle. If you want to explain why the temperature and pressure on the opposite points of the Earth are the same, you construct another function. In this case, it would be a instead of a function which had previously we had taken temperature minus the opposite temperature, you take temperature and pressure and minus the opposite temperature and pressure. And in this case, you get what we call a vector function. And you study this vector function. And again, this is illustrated in my book. And you use winding of this vector around the circle. And you find that the winding number of that circle has to be odd. And that would be a contradiction if it wasn't for the fact that there would be 2 points where have the same temperature and pressure. So the detailed explanation is in the book. David Norouzi asks, is physical reality a manifestation of self-consistent math? This is a good question. I don't have a deep answer. Of course, physical reality should be self-consistent. Whether or not it should be, so that aspect is kind of clear. Why math is so much prominent in physical reality, why math shows up all the time is not completely clear. Of course, math by itself, I would interpret math as self-consistent logical structure. So if you interpret math more generally and more broadly, as saying whatever is self-consistent is math, is a piece of math, then yes, the physical reality will always be described by self-consistent math. But we still don't have a deep understanding of why math is so powerful in describing physical reality. Next question is, some events occurred and exist in the past. Where does the past go? How to find the past? Well, the past in some sense is present. An illustration of the past being present is the fact that the light that we see of the Big Bang today is the Big Bang, the beginning of the explosion of the universe giving rise to our universe. We still are seeing the afterglow. So in some sense, it exists even today in the sense that the light goes around. Now, you might say there's some processes which ended. What about those processes? So the laws of physics in some sense have a formulation which we look at the continuum of space and time, and it's natural to include time in that way of thinking about it. So we think about space and time together in that context. So the answer to that question would be that time doesn't go anywhere, it's there. But perhaps the question is, why do we perceive as if it's gone? And that's a good question. I don't have a good answer to that question. Why is it that our perception is such that the past is past? And of course, one deep aspect of it is related to the following fact in physics, what's called causality. The things in the past affect things in the future, but not vice versa. So in other words, you cannot go back in time in that sense. There's a direction of the arrow of time, and that's kind of related to our perception of time the way we do. But still, it does not have a deep explanation of why we forget about the past in some sense. There's a part of it discussed in my well. Maybe that's too far afield to describe. So let me just stop with that answer. So let's go back to the next question. The question about the galaxies referred to the next slide, where there was a curve that is straight across the, yes. So 3 times or 5 times, right. So the question about the galaxies, right. Okay, so this was the question that was asked. I think I was showing you that when you were trying to describe it, I was trying to describe for you what is the degree of a map means, which by trying to illustrate that winding of that circle near the star. The actual physics is not quite that circle that I drew. I was just illustrating with a mathematical picture for the degree of the map. Okay, the next question, does the number of regions in the endpoint on a circle puzzle assume that each intersection has only 2 lines? Yes, good point. I was assuming generic points on the boundary. So I'm talking about generic. You can of course choose special points on a circle so they will cross at the same point. So I was assuming generically positioned points, so the random points, so that indeed the 3 lines don't cross from the same point. Exactly. Thank you for clarification. That was by Glenn. Next one is can you square the definition of continuity with the theory of multiverses? Well, continuity is there in the physical laws, and multiverses seem to be there in the sense that we have many universes that are consistent in the definition of string theory. There's different definition of what we mean by multiverse, but in general, they're 2 separate concepts a priori. So continuity has no contradiction with multiverse. So we go to the next question. What area of experimental physics research are you most excited for? The question, actually, I'm myself interested in these days on cosmological questions, both the early as well as the late time cosmology. So this question by Brody, actually, I like a lot, because one of the deep puzzles about our universe today is that we seem to have dark energy, and the dark energy is some energy which permeates the whole space, and its value is positive. And this was measured a couple of decades ago. It's one of the amazing discoveries. And because of this dark energy, the acceleration of the Big Bang is actually accelerating even further. And the question is, what is the nature of this dark energy and so forth? And it turns out that the nature of this dark energy is changing potentially over time. And so some of these ideas from string theory that I've been working on actually suggest that the dark energy is not a constant and actually can change over time, and indeed should go down over time. So this observational impact of such a thing would be quite amazing if we can see this by seeing if whether the acceleration of the universe is changing over time in recent epoch or not, and that would be extremely interesting. So that's one of the areas I'm interested in, cosmology. Thank you for the question. And one question by Norris, is there any plan to translate this book into other languages, for example, Spanish? There are so many low-income students which have no access to this type of information in a way that is accessible to them. Have you considered working with your colleagues at the university, education or neural development, or to extend the reach of this fine work with programs such as migrant programs nationally? Excellent question, Norris. That I would love to have a possibility of translating this book to different languages. I wish I knew Spanish to do it, but I don't. So at any rate, I think that it would be great to have this translated, and perhaps I should find people who would be interested in doing this, and I welcome anyone who's interested in doing it. Thanks for the question, and thanks everybody for listening to our discussions as well as the question and answers. I enjoyed the discussions and the questions as well. Thank you very much.
Thank you everybody for coming, and thank you so much, Kamran, for this fantastic presentation, and thanks to Melissa Franklin for that wonderful introduction. Please learn more about this fascinating book and purchase Puzzles to Unravel the Universe at harvard.com. And on behalf of Harvard Bookstore, the Harvard Division of Science, and the Harvard Library, all here in Cambridge, Mass. Have a good night, keep reading, and be well. Thank you so much, guys.
Thank you.